If you walk into a centuries-old cathedral and look closely at the stained glass windows, you might notice something odd. In many of them, the bottom of the glass is thicker than the top. For a long time, this led to a curious myth that glass flows over time like syrup, just very slowly. Wait, what? Is that even possible? Can something that feels so solid actually be flowing? That idea alone is enough to scramble our intuition. After all, we've grown up thinking of the world in neat categories. Solids are solid, liquids are liquid, and gases are gas. Glass sits in windows, it holds water. You can't pour it, you can't stir it, and yet, science tells us glass isn't quite a solid, but it's not a liquid either. So what is it? To figure this out, we have to first question what it even means for something to be solid. A solid, in the classic sense, is a material where the atoms are locked into a crystal lattice, a repeating, orderly pattern that holds everything in place. That's what gives solids their shape, their rigidity, their solidity. Think of salt, quartz, or diamond. Their atoms snap together like Lego bricks in a perfect grid. Liquids, on the other hand, have no such order. Their molecules slide past one another freely, like dancers in a crowded ballroom. So here's the weird part. Glass doesn't do either of those things. Under a microscope, it looks like a liquid. Its atoms are disordered and chaotic. But unlike a liquid, those atoms aren't moving around. They're frozen in place, like a liquid that's been paused mid-splash. This strange in-between state has a name. Glass is what scientists call an amorphous solid, and that term alone is a clue. Amorphous means shapeless, lacking the structure we expect from a true solid. But then, if the atoms aren't moving like a liquid, and they aren't structured like a crystal, how does glass hold its shape? Why doesn't it collapse into a puddle over time? Or, going back to those cathedral windows, is the thickening at the bottom really proof that glass flows? Spoiler, no, it's not. But understanding why it looks that way will take us deep into the world of atomic structure, thermal history, and a concept that might just change how you see the physical world around you. And let's start by digging into that myth about flowing glass. The idea that glass in old windows has slowly sagged over the centuries sounds poetic, almost magical. But it turns out, it's not true. The thicker bottom parts of medieval window panes aren't the result of slow glass rivers. They're the result of how the glass was made. Back then, glassblowing wasn't precise. Sheets were spun or rolled by hand, which created uneven thickness. When craftsmen installed the glass, they usually put the thicker edge at the bottom for stability. That's it. No slow motion melting. Just practical choices made by people centuries ago. But here's where it gets truly fascinating. Even though glass doesn't flow over time, it is trapped in a kind of frozen-in-time state. To understand that, we need to look at how glass is made. When you heat silica, the main ingredient in sand, to extreme temperatures, its molecules move rapidly, like in any liquid. But when it cools, something strange happens. In most materials, cooling allows atoms to fall into place, forming neat, repeating crystal structures. That's how ice forms from water, or how metal hardens after melting. But in glass, the cooling happens so fast, or under such specific conditions, that the molecules don't have time to organize. They're locked in place in the exact disordered state they had as a liquid. Imagine trying to organize a messy room, but someone turns off the lights before you can finish. Everything just stays where it is, chaotic, frozen in mid-move. That's what happens in glass. Its atoms are stuck in a liquid-like arrangement, but they've lost the energy to move. The result is a material that behaves like a solid on the outside but is fundamentally different on the inside. This is where the term amorphous solid comes in. Amorphous literally means without shape. It describes the lack of a long-range repeating pattern in the atomic structure. But this isn't just a poetic label. It means glass doesn't have a well-defined melting point like most solids. Instead, it softens gradually over a range of temperatures. That's why glassblowers can shape it with such artistry. It becomes moldable like warm honey before it becomes a true liquid. And that transition, from rigid to soft to liquid, isn't clean. It doesn't snap from one state to another. This is part of what makes glass so mysterious and so useful. It bends the rules we expect from matter. It blurs the line between solid and liquid, sitting right on the edge of both. And this strange behavior opens the door to even deeper questions, like what defines a state of matter? Are the categories we learned in school just oversimplifications? And if so, how does that change the way we see not just glass, but everything around us? So let's try to make sense of this with a big picture analogy. Imagine atoms like people at a concert. In a perfect crystal like a metal or a diamond, everyone is standing in rows. Ordered, predictable, that's a solid. In a liquid, everyone is dancing chaotically, moving freely. That's liquid behavior. But glass is like freezing the concert halfway through the first song. Everyone's still scattered and disorganized mid-movement. But then the music stops, time freezes. No one gets to finish their dance. They're stuck wherever they were. That's glass at the atomic level. It has the randomness of a liquid, but the stillness of a solid. This frozen disorder has some surprising consequences. One of the biggest is that glass never quite reaches a true equilibrium. It's constantly in a sort of arrested development. From a thermodynamics point of view, it's not the most stable form that silica could take. If you gave it enough time or enough energy, it would try to relax into a more ordered state. But under normal conditions, it's just stuck. That's why some physicists say glass isn't a material. It's a process, a state of matter that's still in transition. That idea sounds strange, but it actually explains a lot. Take, for example, how glass softens. When you heat it, it doesn't melt all at once. Instead, it gradually becomes more and more pliable, like a gummy bear in the sun. That's because different parts of the atomic structure loosen at different rates. There's no single point where it stops being solid and starts being liquid. It's a spectrum. And that's a huge clue that we're dealing with something in between. This also helps explain why glass can be molded with such precision. Think about how a glassblower can take a glowing, almost liquid blob of glass and shape it into a delicate vase or sculpture. That wouldn't work with a regular crystal because crystals melt suddenly and collapse. But glass gives you a graceful transition. It behaves like taffy, not ice. And the fact that we can control that transition so finely is what makes glass one of the most useful materials humans have ever invented. From windows and lenses to fiber optic cables and smartphone screens, we rely on glass precisely because of its weird in-between nature. It's strong yet transparent, rigid yet flexible, fragile yet durable. These contradictions aren't bugs, they're features. They come from the fact that glass is structurally confused, and that confusion gives it superpowers. But here's the kicker. Understanding glass forces us to ask a deeper question. What is a state of matter really? Are there just 3 or 4? Or is the truth way more complex than we were taught in school? That's where things get really interesting. So what is a state of matter? Most of us learned about 3, solid, liquid, gas. Maybe a 4th, plasma, if your science teacher was extra enthusiastic. But the deeper scientists look, the more those tidy boxes fall apart. There are dozens of states of matter, some of them strange, some of them exotic, and some that don't play by any familiar rules. Glass is part of a whole family of weird materials called non-crystalline solids. And once we accept that, we open the door to a whole new way of thinking about matter. Not as a few categories, but as a spectrum. A kind of phase map with strange islands between the big continents. Glass lives on one of those islands. Let's go back to that concert analogy for a second. Picture the crowd again, frozen mid-dance. Now imagine that over thousands of years, tiny parts of the crowd begin to shuffle ever so slightly. Not enough to fully move, but just enough to release stress. That's actually not a bad way to describe what some glasses do. Over geological timescales, millions of years, certain glasses might shift a bit, but not in a way that matters to your windows or phone screen. It's more like a whisper in the atomic fabric. That's how slow it is. Here's another twist. Even the word glass doesn't just describe window panes. There are metallic glasses made from rapidly cooled molten metals. There are polymer glasses, like certain plastics that act rigid at room temperature but soften when heated. And then, there are ultra-stable glasses. Scientists can create them in labs by depositing atoms one at a time in just the right arrangement. These glasses behave more like crystals, even though they're still technically disordered. It's like hacking the freezing process, guiding the dance moves so that the frozen moment is as stable as possible. And here's where it gets mind-bending. Some physicists think that glass isn't just a material. It might be a window into the nature of time itself. Because glass sits in a kind of frozen equilibrium, it helps us study systems that are out of balance, stuck between past and future. In fact, certain models of the early universe suggest that it too passed through a glass-like state as it cooled. So, by studying glass, we're not just learning about windows, We're peering into the physics of frozen time, memory, and the deep structure of disorder. It's almost poetic. A material we use every day to see the world might actually help us understand how the world is. And once you realize that, you'll never look through glass the same way again. But we're not done yet. There's one final insight that pulls all of this together. One that shows how this weird halfway substance is woven into the very fabric of modern life. And once you hear it, you'll understand why glass isn't just not a solid, it's something far more powerful. Let's zoom out and ask, why does this matter? Why should we care that glass is neither fully solid nor fully liquid? Because this strange in-between nature isn't just a scientific curiosity, it's a superpower. Glass has become one of the most versatile materials in human history precisely because of its ambiguity. Its disordered atomic structure makes it transparent, something most crystalline solids can't achieve. That same structure allows it to be shaped with precision, to resist corrosion, to trap light, to bend signals, and to carry data at nearly the speed of light. From medieval stained glass to modern smartphones, glass is everywhere, not in spite of its weirdness, but because of it. Every fiber optic cable that carries internet across oceans, every telescope that peers into the stars, every microscope that lets us see the invisible, every laser, lens, touchscreen, solar panel, all of them rely on the controlled chaos that is glass. It's a material that doesn't follow the rules, and because of that, it bends the world to our needs. Glass shows us that nature isn't confined to simple categories. It's fluid, layered, messy, and full of nuance. Just like curiosity, just like discovery, and just like science itself. So, the next time you touch your phone screen or look through a window, remember, you're not just looking through a solid. You're looking through a frozen liquid that never quite finished becoming one. A substance caught between worlds. And in that strange in-between, we found clarity, connection, and a lens to the universe. If that blew your mind even a little, imagine what else is hiding in plain sight. Hit that like button if you learned something new, share this video with someone who still thinks glass flows like honey, and subscribe to How It Actually Works, the place where science gets intuitive, weirdness makes sense, and your curiosity always has somewhere to go.